It's the Barebones Show, the show that's characterized only by using the default theme for the uninitiated, and this episode is space. It's a slideshow on the space unit because I was just that uncreative, really. And I was also a massive space nerd when I was a lot younger, so I guess that just won't die. So, we start off with space. What is it? It's everywhere. It's just, simply put, a vacuum. It's everything that's nothing. It exists in the gaps between matter, and it is just the simple existence of anything. Everything is space, space is everywhere, and there's no way to avoid it. So, that moves us to our next point, which is a lot simpler to understand, which is stars. We all know what stars are. They are littered around the galaxy, around the universe, and they are at the center of our solar system. And so that leads us to the very simple concept of a war between gravity and fusion, of which these stars are fighting. So every single star in existence is fighting a war between gravity and fusion. Fusion is the explosion of molecules inside it, and the gravity that is trying to compact it down. So, with smaller stars, fusion will always win. And with larger stars, gravity will always win. So that they are burning balls of hydrogen. The hydrogen fuses, as I said, into helium, the helium into beryllium, the beryllium into oxygen, and then finally the oxygen into iron in the larger stars around the end of their lifespan. So when larger stars explode, they become either black holes or neutron stars. Those are the two densest things in the universe, and they cannot be surpassed. And then smaller stars become white dwarfs. White dwarfs, red dwarfs, and brown dwarfs are slow burners, and they will be around until basically the end of the universe, as they burn extremely slowly compared to normal stars, and they don't glow as bright. Which then brings us to star death and supernovae. Supernovae is just funny talk for star death and big star explosions. So, when the war between gravity and fusion is done, gravity always wins with larger stars, fusion always wins with smaller ones, the star will expand, and that is universal. This phase usually lasts around 500 million years, just with our sun, but it does differ from star to star, but it is usually somewhere around 500 million to 1 billion years. So, when larger stars explode, they turn into one of two things, black holes or neutron stars, which then moves us swiftly into neutron stars. They're the second densest things, and only black holes beat it in that regard. They are so incredibly dense that if they were any denser, they would actually become a black hole. So, they contain a lot of mass. So, a single spoon's worth of space would weigh as much as Mount Everest. That is the size of Earth in a cup of coffee. That is every person on Earth compacted into about a square centimeter of space, the size of a sugar cube. And they are only the size of a small city, but can contain as much mass as our sun, or 100 million Earths. So, at the center of neutron stars lies this funny stuff called strange matter. Being that they are the second densest things behind black holes, at the center you can imagine they get crazy hot and crazy dense. So much so that they start pushing electrons into neutrons to become protons. And because of this, they start to push atoms together. And when atoms touch, they collide and they meld together. So it starts forming these sheets, or these rings, these spheres of strange matter that people call nuclear lasagna or strange pasta, because it just resembles lasagna, because scientists are just so good at naming things. But whenever these stars finally explode, they either turn into black holes or they scatter their mass in one hypernova or supernova. So, when this happens, they can spew strange matter in every which way. And when that happens, smaller chunks of strange matter is called a strangelet. And these strangelets are made of strange quarks, which quarks are just what makes up atoms. If you try and pull quarks apart, they just use the energy you gave them to make more quarks. It's not easy to observe a quark on its own because it just kind of can't happen. But there are two types of quarks. There are more, but they just decay into these two types, an up quark and a down quark. And that ultimately determines whether it's a proton, neutron, or electron, determined on what is the combination of the three. So, but there is another type, and that is strange quarks, because strange quarks make up strange matter. And strange quarks are just that, strange. We don't know what they are. In fact, it is entirely metaphysical. We don't know if they exist, but it does work out to exist. So we have no confirmation that they do, but it is very highly likely. So whenever strange quarks touch normal quarks, they make more strange quarks, meaning that strange matter turns normal matter strange, meaning that if a single strangelet were to land on Earth, it would turn the entire Earth into strange matter, which would make it just about the size of a neutron star. It would divide the planet's overall size to the point where it's not even visible from a mile away. So then that moves us on to our last point, which is black holes. It's every space nerd's favorite thing, and every vague talking point of all unhinged lunatics around the globe. So the easiest way that I can describe a black hole is this analogy I once heard from a channel on YouTube called Quasgesagt. So imagine that time and space is a kind of trampoline. Heavier things weigh down the trampoline more and make it bend and dip and divot more. So don't think of a black hole as an extremely deep divot. That's how you think of a neutron star. A black hole is more like a trapdoor or just a hole in the trampoline, because it eats mass without actually gaining any mass. Of course, it gains size, and the mass is all concentrated in the singularity in the middle. It's an infinitely small point containing all mass of the black hole, but of course, it's not able to be seen. And what's funny about black holes and what makes them so cool is that they bend light around them, as nothing can escape a black hole, even light, which actually makes black holes invisible. The only reason they're called black holes is because space is dark, it's black, there's no light being shown, so it just takes on the appearance of whatever's around it. But for the light that does somehow escape, it does enter your eyes and it kind of bends around. So if you were to enter the event horizon, or the point of no return, in a black hole, that's the point in which you cannot leave, then it would, if you look to your left, you would see the right side of your body. If you look to the right, you'd see the left side of your body, and forward, you would just see the back of your head. And so to the outside world, it would just seem as you just freezing and then slowly fading away, as your mass gets consumed by the black hole, and it is then nowhere to be seen. And of course, there is a theory about white holes and all mass that enters black holes being spewed out somewhere across the universe, but that theory has little to no merit. And so that is the end of my slideshow, and thank you for listening, and have a nice rest of your day. Thank you.